Graphs of exponential functions. Like with linear functions, the graph of an exponential function is determined by the values for the parameters in the function's formula. To get a sense for the behavior of exponentials, let us begin by looking more closely at the function f of x equals 2 to the x power. Let's think a table of values for this function. Notice that this function is positive for all values of x. As x increases, the function grows faster and faster, the rate of change increases. As x decreases, the function values grow smaller, approaching 0. This is an example of exponential growth. Looking at the function, g of x equals half to the x power. Note, this function is also positive for all values of x, but in this case grows as x decreases and decreases towards 0 as x increases. This is an example of exponential decay. You may notice from the table that this function appears to be the horizontal reflection of the f of x equals 2 to the x table. This is, in fact, the case. F of negative x equals 2 to the negative x power equals 2 to the negative 1 raised to the x power equals half raised to the x power equals g of x. Looking at the graphs also confirms this relationship. Consider a function of the form f of x equals ab to the x power. Since a, which we called the initial value in the last section, is the function value at an input of 0, a will give us the vertical intercept of the graph. From the graphs above, we can see that an exponential graph will have a horizontal asymptote on one side of the graph and can either increase or decrease depending upon the growth factor. This horizontal asymptote will also help us determine the long-run behavior and is easy to determine from the graph. The graph will grow when the growth rate is positive, which will make the growth factor be larger than 1. When it's negative, the growth factor will be less than 1. Graphical features of exponential functions. Graphically, in the function f of x equals ab to the x power, a is the vertical intercept of the graph. B determines the rate at which the graph grows. When a is positive, the function will increase if b is greater than 1. The function will decrease if 0 is less than b less than 1. The graph will have a horizontal asymptote at y equals 0. The graph will be concave up if a is greater than 0, concave down if a is less than 0. The domain of the function is all real numbers. The range of the function is 0 to infinity. When sketching the graph of an exponential function, it can be helpful to remember that the graph will pass through the points 0, a, and 1, a, b. The value b will determine the function's long-run behavior. If b is greater than 1, as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches 0. If 0 is less than b less than 1, as x approaches infinity, f of x approaches 0, and as x approaches negative infinity, f of x approaches infinity. Example 1. Sketch a graph of f of x equals 4 multiplied by 1/3 to the x power. This graph will have a vertical intercept at 0, 4 and pass through the point 1, 4/3. Since b less than 1, the graph will be decreasing towards 0. Since a is greater than 0, the graph will be concave up. We can also see from the graph the long-run behavior. As x approaches infinity, f of x approaches 0, and as x approaches negative infinity, f of x approaches infinity. To get a better feeling for the effect of a and b on the graph, examine the sets of graphs below. The first set shows various graphs where a remains the same and we only change the value for b. Notice that the closer the value of b is to 1, the less steep the graph will be. In the next set of graphs, a is altered and our value for b remains the same. Notice that changing the value for a changes the vertical intercept. Since a is multiplying the b to the x term, a acts as a vertical stretch factor, not as a shift. Notice also that the long-run behavior for all these functions is the same because the growth factor did not change and none of these a values introduced a vertical flip. Example 2. Match each equation with its graph. f of x equals 2 multiplied by 1.3 to the x power, g of x equals 2 multiplied by 1.8 to the x power, h of x equals 4 multiplied by 1.3 to the x power, k of x equals 4 multiplied by 0.7 to the x power. The graph of k of x is the easiest to identify since it is the only equation with a growth factor less than 1, which will produce a decreasing graph. The graph of h of x can be identified as the only growing exponential function with a vertical intercept at 0, 4. The graphs of f of x and g of x both have a vertical intercept at 0, 2, but since g of x has a larger growth factor, we can identify it as the graph increasing faster. Transformations of exponential graphs. While exponential functions can be transformed following the same rules as any function, there are a few interesting features of transformations that can be identified. The first was seen at the beginning of this section, that a horizontal reflection is equivalent to a change in the growth factor. Likewise, since A is itself a stretch factor, a vertical stretch of an exponential corresponds with a change in the initial value of the function. Next, consider the effect of a horizontal shift on an exponential function. Shifting the function f of x equals 3 multiplied by 2 to the x power 4 units to the left would give f of x plus 4 equals 3 multiplied by 2 to the x plus 4 power. Employing exponent rules, we could rewrite this f of x plus 4 equals 3 multiplied by 2 to the x plus 4 power equals 3 multiplied by 2 to the x power multiplied by 2 to the 4th equals 48 multiplied by 2 to the x power. Interestingly, it turns out that a horizontal shift of an exponential function corresponds with a change in initial value of the function. Lastly, consider the effect of a vertical shift on an exponential function. Shifting f of x equals 3 multiplied by 2 to the x power down 4 units would give the equation f of x equals 3 multiplied by 2 to the x power minus 4. Graphing that, notice it is substantially different than the basic exponential graph. Unlike a basic exponential, this graph does not have a horizontal asymptote at y equals 0. Due to the vertical shift, the horizontal asymptote has also shifted to y equals negative 4. We can see that as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches negative 4. We have determined that a vertical shift is the only transformation of an exponential function that changes the graph in a way that cannot be achieved by altering the parameters a and b in the basic exponential function f of x equals a b to the x power. Transformations of exponentials. Any transform exponential can be written in the form f of x equals a b to the x power plus c, where y equals c is the horizontal asymptote. Note that due to the shift, the vertical intercept is shifted to 0, a plus c. Example 3. Sketch a graph of f of x equals negative 3 multiplied by half to the x power plus 4. Notice that in this exponential function, the negative in the stretch factor, negative 3, will cause a vertical reflection, and the vertical shift up 4 will move the horizontal asymptote to y equals 4. Sketching this as a transformation of g of x equals half to the x power, the basic g of x equals half to the x power, vertically reflected and stretched by 3, vertically shifted up 4 units. Notice that while the domain of this function is unchanged due to the reflection and shift, the range of this function is negative infinity, 4, as x approaches infinity, f of x approaches 4, and as x approaches negative infinity, f of x approaches negative infinity. Functions leading to graphs like the one above are common as models for learning and models of growth approaching a limit. Example 4. Find an equation for the function graph. Looking at this graph, it appears to have a horizontal asymptote at y equals 5, suggesting an equation of the form f of x equals ab to the x power plus 5. To find values for a and b, we can identify 2 other points on the graph. It appears the graph passes through 0, 2, and negative 1, 3, so we can use those points. Substituting in 0, 2 allows us to solve for a. 2 equals ab to the 0 power plus 5. 2 equals a plus 5, a equals negative 3. Substituting in negative 1, 3 allows us to solve for b. 3 equals negative 3, b to the negative 1 power plus 5. Negative 2 equals negative 3 divided by b. b equals 3 halves equals 1/5. The final formula for our function is f of x equals negative 3 multiplied by 1.5 to the x power plus 5.